Okay. Thanks, Dominic, for the introduction. So hi, everyone. I'm Deevashwer, and in this presentation, I'll be talking about SecFloat, which is a 2PC library for accurate floating point. This is a joint work with my excellent colleagues from Microsoft Research, Anwesh, Rahul, Divya, Nishanth, and Aseem. So let's get started. Okay, so first of all, what is 2PC? So 2PC is a very powerful cryptographic primitive which allows two mutually distrusting parties to evaluate arbitrary functions on their secret inputs without revealing anything beyond the output. So although like this F can be an arbitrary program, floating point programs are of special interest because floating point is used widely in software for emulating real, like computation on real numbers. So this brings a natural question forward, is that how to securely evaluate floating point programs. So currently there are two options. The first one is to take 2PC protocols for floating point, and this option has some nice properties. For instance, it's a plug-and-play solution. From plug-and-play, I mean that in your floating point program, you have floating point operations. You can just replace them with the corresponding 2PC protocol. And this option also is accurate because you're not changing F. So you're exactly computing F. But the problem is that the overheads are intractable, or it's like widely believed that they are completely intractable. So no one really looks at this option that much. The second option is to consider fixed point approximations, which have great performance. So that's where most of the focus has been. But there's this float to fixed conversion, which is required for floating point programs, which is pretty janky. So in the sense, like, first, this leads to a precision loss because you're now not computing F, you're computing F prime, an approximation. The second problem is that this conversion is only available for a few applications, like machine learning, for instance, and there's no general tool which you can use to go from a floating point program to a fixed point approximation. The third problem is that this process is quite painstaking, in that if you've ever worked with fixed point code, you would realize that it's a debugging nightmare to deal with it. You have to choose scale, bit widths. There are a lot of moving parts. And finally, an efficient conversion is not even always possible from float to fixed. So you could even end up with a fixed point approximation which is not efficient, which does not even make sense. Okay, so despite all of these problems, most of the focus has been on this option 2. But in this work, we take a different approach and focus on option 1, and actually show that floating point 2PC can actually be practical. Okay, so let's look at the lay of the land. So these are what are the existing solutions for secure floating point right now? So the first option is to take a clear-text floating point library, which has nothing to do with security, and run it with some generic 2PC protocol. For an example of this is SoftFloat, and you run this with CVMCGC. So as you'd expect, the precision is as precise as standard float, but the performance is pretty terrible with a semi-honest 2PC backend. And the reason for this is first that you're using a generic 2PC, and the other problem is that these floating point algorithms were not designed keeping 2PC in mind. They were designed for CPUs. The second option is to consider prior works specifically for secure floating point. And while these works have much better performance, like 300x better performance than the generic 2PC solution, the precision is very poor. So for instance, for a simple example like x by sine pi x, where x is close to 0, the state-of-the-art outputs a division by 0 error, while the output should have been 1 by pi. So clearly, both options are inadequate, and this is where SecFloat comes in, and it provides protocols which are as precise as standard float, and the performance is also even better compared to the imprecise floating point works. So in more detail, we provide novel 2PC friendly and provably precise floating point algorithms, which are up to 7 orders of magnitude more precise than prior work on secure floating point. And we implement these algorithms in a semi-honest 2PC library called SecFloat, which provides up to 2 orders of magnitude better performance compared even to the imprecise prior work. And to demonstrate the practicality of SecFloat, we consider 2 applications. The first is privacy-preserving proximity testing, and the second is secure machine learning inference. And for both of these applications, we show nice improvements in performance as well as precision. Okay, so for the rest of this talk, this is my agenda. I'll first go over SecFloat's 2PC friendly design, and I'll go over the primitive operations as well as math operations. Next, I'll go over a part of our evaluation, starting with micro benchmarks, and then I'll focus on one of our applications, which is secure ML inference. And for this application, I'll show that fixed point approximations are inadequate, and the floating point that we design is practical. And finally, I'll conclude with some directions for future work. So first, starting with the 2PC friendly design. So in this section, I'll basically compare and contrast with the existing standard libraries. I'll mention how they, what properties they have and how we design SecFloat to be different. Okay. So first, looking at primitive operations. So in the standard libraries for primitive operations, more conditional statements are involved. This is fine because in CPUs, you only have to execute one branch, so it does not matter. But in 2PC, all conditional branches have to be evaluated, because any branch which is not evaluated would leak information. So we designed SecFloat to have fewer conditional statements. The second point of difference is that standard libraries have larger and standard bit widths, like 16, 32, and 64. This is great because 16, 32, and 64 have native support on CPUs. So they are fine using them, but we designed SecFloat to have smaller and non-standard bit widths, like 10 instead of 16, 17 instead of 32, and so on. And we do this without any loss in precision. So we are guaranteeing the same precision. And this is important because 2PC cause scales linearly with bit width, so the smaller the bit width is, the more performance you get. And with these changes, SecFloat offers a 2.4x to 6.1x improvement over SoftFloat, which is a standard library, with the same backend. And after these, with these improvements, the relative cost of these operations are as follows. So addition is 11 times more expensive than comparison. So looking at these costs, you would realize that you would not see the same performance characteristic in CPUs. So since the 2PC relative cost is very different in 2PC compared to CPUs, our design of math operation is also very different, because math operations ultimately rely on primitive operations. Okay? And the final point of difference in primitive operation is that standard libraries have specialized algorithms for different IEEE formats. And in contrast, SecFloat has one general algorithm for arbitrary floating point representation. And this generality is quite useful in designing our math floating point algorithms, as I'll discuss in the next slide. Okay. So looking at, now moving on to the math operations. So our math operations also follow this three-step procedure like standard libraries. First, there's the range reduction step, which reduces the range of the input. Then there's a polynomial evaluation on that. And finally, the output of polynomial evaluation is adjusted in an output compensation step. So we don't have to go into the details of all three steps, but the important point is that all steps introduce some error into the computation. So we have to do this computation in some higher precision so that the errors which are introduced can actually be accounted for. And I also have this relative cost table from the previous slide, just for reference. Okay, so first, the standard libraries for math operation use 64-bit doubles for the intermediate operations because they have native support. But the 64-bit is actually quite large, and this is expensive for 2PC. So in contrast, we use a custom 36-bit floating point representation for intermediate operation, which is greater than 2 times better in performance compared to doubles. And as a result of using this much lower precision representation, we have to design novel range reduction techniques because the existing range reduction techniques have way too much error for this, this imprecise representation. And so I was talking about generality before. So this 36-bit floating point representation is not supported by any standard library, and they don't have a general algorithm. But the general algorithm that we have directly makes it possible to do these operations. The next point is that standard libraries have high-degree polynomials. So they involve many floating point additions and multiplications. As you can see in the table, they are quite expensive. So we instead use low-degree splines. And so basically, we have replaced most of the floating point additions and multiplications with floating point comparisons, which you can see are much cheaper comparatively. And moreover, in addition to using floating point comparisons, we carefully choose the spline knots in our splines so that to identify the interval in which the input is lying, we only have to do integer comparison on less than equal to 8 bits instead of doing full-fledged 36-bit floating point comparisons. And even for the remaining floating point addition and multiplication, we use cheaper imprecise variants. So we realized that for intermediate computations, we don't need the most precise version of these arithmetic operations. Finally, the range reduction in standard libraries use floating point operations because they are natively supported. But we design range reduction to only use fixed point operations because they are cheaper with 2PC. Okay. Now moving on to the evaluation. So first, let's look at the micro benchmarks. So I have the micro benchmarks for a primitive operation, which is multiplication, and a math operation, which is sign. And here, first, let's look at the black rows, which represent the precise works. So here, for multiplication, we have a 46x improvement in runtime. And for sign, the improvement is 3 orders of magnitude compared to the precise baseline. And in red, I have the imprecise baseline over which we still have 4x improvement. In terms of rounds, the prior works can be evaluated either with gobble circuits or with GMW. So if it's gobble circuits, then the rounds are just 2. But compared to the GMW baseline, our rounds are comparable. Okay, now let's look at our application. So we look at secure machine learning inference in the context of privacy-preserving web advertising, which has recently garnered a lot of attention from Google and Microsoft. And for this application, one model which is used is this industrial relevance model, which is a fully connected neural network with 3 hidden layers. And when we took this model and ran this state-of-the-art flow-to-fixed converter on this model, we realized that it failed completely. So from failing completely, I mean that for each scale, so this converter tried each scale, and for each scale, the fixed point model output was garbage. So for for smaller scales, the precision was too low, and for larger scales, there was an overflow in 64 bits. And this was happening because the dynamic range of weights was quite large, from 10 to the minus 7 to 10, and the range for the intermediate activations was even larger. In contrast, when we ran the same model with SecFloat, we could evaluate it without any of this like scale determination or anything. We could run it directly without any accuracy loss in just 18 seconds and with 4.7 GB of communication. If we also benchmarked how much communication would be required with prior work in floating point, which is also imprecise. The difference in communication was 8.8x. So this shows that SecFloat enables practical secure inference of such models for the first time. Okay. In summary, we designed novel 2PC friendly and precise floating point algorithms which offer large improvements over prior work, up to 7 orders in precision and up to 3 orders in performance. This shows that precise secure floating point can actually have practical performance. Although we have taken a significant step forward in this direction, a lot of work is still needed for wide adoption so that it can be made practical for a lot of applications. So I have some directions for future work here. First is that extending SecFloat to be maliciously secure or to the end party situation. It's actually pretty straightforward because all of our algorithms just use simple operations which are supported by any of the MPC or maliciously secure MPC or 2PC libraries. The second is to improve the rounds of our floating point protocols. So we did not focus that much on improving rounds in this work, and that could be an interesting direction. The third is to extend math operations to 64-bit doubles. So our primitive operations support arbitrary representations, but our math operations are limited to 32-bit float. And finally, we think that SecFloat can be useful in other areas of privacy-preserving machine learning. That's it, and our paper and code are publicly available, and we hope you check them out. That's it. Thank you for your attention. Okay. So, any questions?
Yeah, all right, thank you so much. Awesome talk. Any questions from the audience?
Yeah, so this is a bit of a broad question, but I'm curious why you think in your setting and in the typical CPU hardware setting, you end up with such different cost profiles, because at least somewhat naively, I'm thinking of both of these settings as requiring a Boolean circuit. So yeah, why the huge difference in the cost profile?
I think that the difference majorly comes from, so in the floating point is really expensive because of a normalization operation. So you basically, so normally in 2PC, you would do arithmetic operations in an arithmetic domain, and for Boolean operations, you would go to a Boolean domain. And there, I guess in CPU, that is just as good because you can have both operations natively implemented, and there's not that big of a conversion cost. But for normalization in 2PC is actually quite expensive. So for addition, you saw it was 11C, right? 11 times. I think around 10 of that comes from just a normalization. Like it's a very expensive operation which requires determining the most significant non-zero bit. And that is expensive in 2PC, and I think future works can improve that and actually reduce the huge gap that exists right now.
I see, yeah, thanks.
Was that the end? Or? Outside. Then, if there aren't any more questions from the audience, I don't think. Oh wait, we have one from the chat. No, never mind. Nothing from the chat. Then I would maybe like ask one of my questions. So you mentioned maybe the extension to double precision. Could you just like go a bit more into that? What you would like plan on doing and what you think would be like successful there?
So I think like that would be a bit challenging with our approach. So right now for 32-bit floats, we are doing an exhaustive evaluation. So we are basically testing, like that's how we formally verify that our implementations are correct. We go over all possible outputs and see that they work, but that's impossible to do for 64-bit doubles right now. So we need, I think like some nice like advancement is required in verification technologies to actually make it happen for 64-bit doubles. I think that's a challenge even for, even in the floating point community to make it happen.
All right, thank you so much. Awesome talk. Give it up again for Deevashwer with the talk.